We are on module 8, lesson 2, and we're going to talk about duality, the duals of Boolean functions, and we will close this lesson with generalized abstract Boolean algebras. What is duality? The identities in table 5 come in pairs except for the law of double complement and the unit and zero properties. To explain the relationship between the two identities in each pair, we use the concept of dual. The dual of Boolean expression is obtained by interchanging Boolean sums and Boolean products and interchanging zeros by ones. So as long as we keep that in mind, finding dual to a Boolean expression or a Boolean function is not at all difficult. I'm sorry. So we're going to start talking about example 11. It's finding the duals of x times y plus 0 and x bar dot 1 plus y bar plus z. So as we have talked about, the location of x, y and 0 will be the same. The only change is going to be you will change dot by a plus and plus by a dot, and zeros will be changed to 1 and ones will be changed to 0. So for the first one, I will say y dot 1 and I change the plus to a dot and I change the 0 to 1, whereas x dot will be changed to x plus. So that's the dual of the first expression. And then I look at the second expression. Remember, complements don't change. So when I'm looking at the complements, I'm going to keep it as complement of x. The dot, I will change it to a plus. The 1, I will change it to a 0. The plus, I will change it to a dot. And then I will keep y complement. The plus, I will make it a dot and then z. And what I will tell you, keep this x bar plus 0 inside parentheses as well. And the reason I'm doing it, when we have the dot between x bar and 1, we know that we will compute that first. So in order to make sure that we are following that order of operation, I'm going to keep x bar plus 0 after I found the dual inside parentheses. And that answers my question and is as simple as that. So construct an identity is our example number 12. So we are constructing an identity from absorption law, which is x times x plus y equal to x, by taking the duals. So remember, to do the same thing, you will keep x, you will keep x and y inside parentheses as well. Change the first dot to a plus and change the plus inside the parentheses to a dot, and that will equal to x. And remember what we got. We started with one of the absorption laws that was a plus following a dot, and by taking the dual, we got the other absorption law, which was taking a dot following a plus. Answers our question. We'll do a couple of exercises in our problem section about duality, but let's talk about the generalized concept of abstract Boolean algebras. So in this section, we have focused on Boolean functions and expressions. However, the results we have established can be translated into results about propositions or results about sets. Because of this, it is useful to define Boolean algebras abstractly. Once it is shown that a particular structure is a Boolean algebra, then all results established about Boolean algebras in general will apply to that particular structure. Boolean algebras can be defined in several ways. The most common way to specify the properties that operations must satisfy, as done in definition 1 in the following page. So what is a generalized Boolean algebra? A Boolean algebra is a set B with two binary operations, OR and AND, elements 0 and 1, and a unary operation, complementation, such that the following properties are all true for any x, y, z in the set B. So x OR 0 is x, x and 1 is x, that's identity law. X OR complement of x is 1, x and complement of x is 0, that's complement law. X OR y or z is x OR y or z. X and y and z is x and y and z, that's associative law. X or y is equal to y or x. x and y is equal to y and x, that's commutative law, and the or distributes over and the and distributes over or in other words, x or y and z is x or y and x or z, x and y or z is x and y or x and z. As long as I'm following the laws of identity complement, associativity, commutativity, and distributivity, then we call the, or, and complement as a generalized abstract Boolean algebra. So let's do a couple of examples. This section is indeed very simple. We are going to find out the duals of the given Boolean expression. The first one is pretty simple. It's just x plus y. So the dual of this expression is going to be x dot y. Then it is xy complement. So if you want to understand, you will first write it as x dot y complement. So when I find the dual of this expression, I'm going to go ahead and change the dot by a plus. Never change the complement, it stays as a complement. So you get x plus y and then take the complement of that. The following expression, I have x dot y dot z. I always write it using the dots so that it makes understanding a little better, and also it helps you understand the order of operation, which one you should do first. Now let's start taking the dual of this expression. So change all the dots by pluses, so you get x plus y plus z, and I will put that inside parentheses because that should be executed first. Similarly, you get x plus y plus z under the complement, and then this portion should be dotted with the first portion. So the x dot y dot z plus x dot y dot z complement becomes x plus y plus z dot x plus y plus z's complement. The fourth one is x z bar plus x dot 0 plus x bar dot 1. So I will write it as x plus z bar, put it inside parentheses, change the plus to a dot, x plus 1, taking the dual, changing dot to plus and 0 to 1, and then put it inside parentheses. Then the plus should be a dot, and finally I do x bar, dot is plus, and 1 becomes 0. And that answers my question for finding the dual of the given Boolean expression. And that will be the conclusion of this section. And we will go to Module 8, Section 3, where we're going to talk about expression of Boolean functions.